We move on to another important topic, which is the work energy theorem. This is an important theorem, as we will see in this chapter, that allow us to solve physics problem. Consider this situation. We have this mass, we have this applied force, the net external force F net. The object is moving with some initial velocity, Vi equals V naught, the initial velocity. After a displacement delta x, the object now has a final velocity Vf, V final, equals to V. The work, as we learned it, the net work, is equal to the net force multiplied by the displacement. So you have the net force multiplied by the displacement. This is equal to the net work in this motion. Now, we know from Newton's law, from chapter 4, that the net force is equal to mass by acceleration. So it is max. And we know from the kinematics equations, V final squared equals V initial squared plus 2ax. We know that ax equals V squared minus V initial squared divided by 2 when we solve this equation for ax. So now, if you substitute here for ax this value, we arrive at this important conclusion. The net work is equal to half mv squared minus half mv naught squared. This is a very important conclusion. The quantity half mv squared is the kinetic energy of the object. This is the kinetic energy of the object, the final kinetic energy here at the final position. And half mv naught squared, this is the initial kinetic energy that the object has at the initial position. What this equation is telling us, it is saying simply the only way to change the kinetic energy from its initial value to its final value is to have work, to do work on it. Okay? That's the only way to change the kinetic energy. We need to do work. Consider, for example, you are driving your car. The traffic light turns from green to red, and now you want to stop your car. So originally, your car has some kinetic energy, half mv squared. When you stop the car, V is 0. So the final kinetic energy in this case would be 0. So naturally, in order to achieve that, you will need a negative work. You have a minus sign here. You will need a negative work. And usually, this is what we do. The negative work is done by friction force. When you press on the brake pedal in your car, when you press on the brake pedal to bring the car down, to slow it down, to stop it, as the traffic light turns from green to red, the friction force acts between the mechanical parts of the tires and the tires to stop the motion. Friction is always opposite to motion in kinetic situations. So yes, the work done will be negative. Another example, I will use the same example. The traffic light turns into green, and now you want to start moving. The only way to change the kinetic energy, the only way to change the kinetic energy is to exert work. Usually the force from the engine by burning fossil fuel, the force from the motor of the car will start acting as you press on the gasoline pedal. Burning gasoline will give us the needed force, and with displacement, this will be the work, the net work. This allows us to change the kinetic energy such that the car will accelerate and move forward. So now I hope you have a good understanding of the work energy theorem. In plain English, you will always need to do work in order to change the kinetic energy. You cannot change the kinetic energy without work, period. Okay? This is a very important theorem in physics, and once we understood it well, it helps us to solve problems. Kinetic energy is a form of energy. All forms of energy are measured in joules. So like any other form of energy, the unit for kinetic energy is joule, which is equivalent to 1 kilogram meter squared per second square. So the change in the kinetic energy, we may write it as kinetic energy final minus kinetic energy initial, or use delta. This is a mathematical symbol. We know delta. Delta means change in kinetic energy. So the net work is equal to the change in the kinetic energy. Consider this situation. The hammer here is moving and knocking on this nail. So the hammer has kinetic energy. Because it has kinetic energy, it can do work because of this relationship between work and kinetic energy. So as it hits the nail, it is stopped. So kinetic energy now is zero because there is no motion. What happens? So all the energy now is transformed into work, and because of this work forced by displacement, because of this work, the nail goes into the wood. Okay? So we understand this interplay between work and kinetic energy in this example. A block slides at constant speed down a ramp while acted on by three forces: its weight, the normal force, and the kinetic friction. The combined net work done by all three forces in the block equals zero. Is this a true or false statement? Let's think together. Since it is a constant speed means no acceleration, right? If no acceleration, then the net force is zero. If the net force is zero, then the force that is driving the block forward is equal in magnitude to the kinetic friction force, which is acting in the opposite direction. They are equal in magnitude, right? So whatever work is done by the force, it is equal in magnitude to the work done by the kinetic friction. The work done by the force is positive. The work done by the kinetic friction is negative. Because they are equal, the total is zero. For the normal force makes 90 degrees with the displacement. So the work done by the normal force is zero. So from this discussion, we conclude that yes, this statement is true. The combined net work done by all three forces on the block is equal to zero. Again, a block slides at constant speed down a ramp while acted on by three forces: its weight, the normal force, and kinetic friction. Each force does zero work on the block as it slides. This statement naturally is not correct because friction force is not zero. Friction force is negative. As for gravitational force and normal force, both are perpendicular to the displacement. So yes, these forces will make zero work. But friction force is not zero work. It makes negative work. We move on to conservative and non-conservative forces. The best example of a conservative force is gravity. By conservative force, we mean the force that when acted on an object over a round trip, the total change in energy is zero. For example, here, as this lady climbs up, she is doing work. She is doing work. When it reaches here, the energy now that she exerted is all converted into potential because there is no motion, no kinetic energy. The energy now is all potential. When she jumps down, the potential energy converts back into kinetic energy. The total energy involved here, the change in the potential energy, is equal to the change in the kinetic energy for the trip up. If you add this energy up to the energy down, the total is zero. Okay? So the force of gravity is a conservative force, and this is how we define it. Now, we don't care whether it is along this path or along this path, as long as there is no friction. The assumption this is smooth, no friction. So the change in the energy for this round trip or for this round trip will be zero. Always when you have such a situation, the force is called a conservative force. The field, the gravitational field, is called a conservative field. On the other hand, if you think of friction, friction is the best example for a non-conservative force. Friction always opposes motion. If the motion is to the right, friction is to the left. If the motion to the left, friction is to the right. Because of that, over a round trip, friction adds up into a negative value. Because of that, we call a friction force non-conservative force. This example helps us to understand more the difference between the conservative and the non-conservative force. Here, if you drag this book from A to B, from B to C, from C to D, and back to A, the friction force will add up. At the end, it has a negative value, not zero. While here, the tip from ground surface up and then back to ground, the total change in energy, the total change in work is zero. So this is a conservative force. This is a non-conservative force. Friction is a non-conservative force. Now, when you add up both works for conservative and non-conservative forces and put them in the work energy theorem, so the work done against non-conservative force plus the work done against conservative force, when you add them, they add up to the change in kinetic energy. That is to say, the net work is equal to the change in kinetic energy.